All right, good morning. Another physics reaction video for the Physics Teachers Are Awesome project. Today I've been doing some work lately using some Lagrangian mechanics, and I wanted to find some interesting explanations of doing Lagrangian mechanics. So I literally did a search for Lagrangian mechanics examples and found this. This is actually somewhat old. I think about maybe 4 years old. And just I listened to like the first 5 seconds to make sure that it's not about the mathematical Lagrangian approach, which is also cool, like things like Lagrange multipliers and things like that. I'm pretty sure this is what I'm looking for, so here we go.
Hi, my name's Bryony. I'm a condensed matter physicist. I completed my degree under the supervision of Professor Michelle Simmons, who won 2018 Australian of the Year.
Cool.
So in this topic, we're looking beyond the basics at Lagrangians and Hamiltonians. So I'm going to start off by introducing you to this idea called the Lagrangian. But even before we...
So just going to talk about the setup. Really interesting lighting, right? You can tell that there's a very well illuminated prop, I guess, and of course you can see her really, really well. It doesn't look like she's going to be writing anything. I'm curious to see if any graphics come up and wonder whether there's any like post-processing going on here. So yeah, exciting. I'm not 100% sure what is going on here. Maybe this is like a pendulum with a movable point or something. Seems like a complicated problem to start out with. So I'm not sure what's going on with this track, so we'll see.
We get into that, I want to step back and think about what do we mean when we talk about like describing a system. So if we have a system, be it a pendulum, a car rolling along a track, anything, the way we describe it is by its position, its velocity, and its acceleration. And all those things normally we find through the equations of motion. So
cool. Have
a look at this system here. This is a cart, so a large mass.
Wait, I don't understand. Where is this hanging? It doesn't, can't see very well, but this rope, I'm not sure exactly where it's dangling. Oh, there's 2 tracks. Maybe it's dangling right in the middle. Oh, that's really cool. Okay, let's get it going again here.
On this track, we're going to assume it slides without friction. And underneath it, we can see there is a string with a mass tied at the end.
Cool.
So we can see that if I bring this back here and I then push it forward, you can see that as this string moves, that it affects the motion of the cart. As the cart moves, it affects how the mass at the end moves. So
oh, look at that.
A system like this is pretty complex. If I asked you to derive for me the position, velocity, acceleration as a function of time for this, could you do it? Because if you could, please let me know, because I haven't even bothered trying, because it would be a horrendous problem. So instead, we need to have a
That's awesome.
way, a nice and prettier way. So in the 18th century, a dude called Pierre-Louis Maupertuis came up with this idea that is any physical system will follow a path of least.
All right, so we've got some post-processing here. And this is literally word for word what she just said. So what I often wonder about these things is, is she reading a script and so that's why this is nailed? Or did she, when she did the post-processing, just kind of listen to herself and say, ooh, that was a good sentence, and type it in? Either way, I mean, it's so great, right? When you think about just making sure the students are really consuming this information and really trying to get a handle on it, to hear it, to see it, to have it read, it's super useful. And of course, here we see the incredible usefulness of the black background, because the letters are just so crisp, and we're not struggling to read it at all. Very cool.
Length. Basically, Mother Nature is lazy and does as little work as possible. So it actually turns out that you can generalize this not just physical systems traveling along a path. You can actually generalize it to anything. It's principle of least action, which is that any system undergoing some change, whatever, it will behave in such a way that the action is minimized. So we can define action this fancy way, with S is the integral from T1 to T2, where T1 is like our initial time, T2 is the final time, so that would be T1, and then maybe T2 as it's moving. L is our Lagrangian, which I'll be discussing later, and dt is obviously time. So this equation looks scary, but it's actually really beautiful and combines a lot of really cool things in physics. So don't be scared of it, and even more to...
Just want to let you know that the steam's just been turned on in my my building. That's all the noise in the background. Just want to stop here for a second. So what she said was super, super interesting, right? That any change has an action that is going to be, the change in the action is going to be minimized. For Lagrangian stuff, there's a very, very particular thing that you put right here that turns out to be minimized. And so what I wonder is, if you don't define the action, can that statement be true like all the time? As long as you leave the definition of the action totally undefined for the moment, can you just say, look, there's this thing, what the heck, we'll call it the action, whose change is minimized. I suppose that's true. And then we have the hard time of explaining to students why, okay, but for these problems, what we're going to use is the kinetic energy minus the potential energy, which seems to come out of nowhere, right? Because students are like, what do you mean? You're subtracting those two? We add them. That's total energy. So the fact that we subtract them, it takes a while to think about and try to figure out why that's true. Now you can go through the motions and show, aha, look, you get Newtonian's laws of motion this way. So trust me, it works. But I'm curious to see, probably not in this video, it's only 10 minutes long, whether she really hammers that or not. So very, very cool.
Don't be scared of it, because we're now going to put it away and just look at this L. So this L is this magic Lagrangian. The thing that I've been promising will explain this a lot nicer than our ugly Newtonian mechanics can. So our Lagrangian actually is not defined using our normal position, acceleration, velocity naturally. You can start with a function and then do some cool tricks to it to turn it into a Lagrangian. And if you've done any engineering or economics, you've probably played around with that. But the nicest way that we do it in physics, at least, is by the energy. So when Maupertuis first defined his principle, he used this quantity T and said this quantity T is minimized, blah, blah, blah. But it turns out this quantity T is actually our kinetic energy. So we can then define our kinetic energy. Instead of using K, we use T, because we like to be special sometimes. We also use involve our potential energy. Our potential energy, in this case, we'll take as V. So we can define our Lagrangian quite simply as L equals T minus V, where T is our kinetic energy and V is our potential energy. So before we get started...
So I was watching her eyes there to see if she was reading. It really didn't look like she was reading, because her eyes weren't doing it at all. Like if I read the screen, if I go from that side to that side, my guess is you can see my eyes moving. I'm not looking at myself, so I can't tell. Let me look at myself. I can't see myself. So I don't think she's reading. I think that the post-processing figured out what to put on the screen after listening to what she said, which is great, right? I mean, again, it sort of nails it. Now, I don't know what's going on here. My guess is, because this looks like a cursor, maybe we're going to see some drawing now, or handwriting. Let's see.
Started into actually finding the Lagrangians. I'm just going to give you a little note on some notation. So we remember from earlier in this course that we can express the velocity and the acceleration as derivatives of the position. So we know that our velocity is ds dt, where s is our position.
Ooh, really, really good pressure-sensitive digital device here. Notice that it's literally dim here and bright there. So pressure sensitivity, you can tell the different hardware and software do it differently. So for example, OneNote doesn't actually ever do this. All it ever does is thin or thick. And so the actual color of the line, let's say you were to use white on black, it's always exactly pure white. It's just that the line gets thinner, whereas this is more like I'm trying to think what's software that does this best. Some of the drawing programs, for example, will do exactly this, where you can see this. And so I actually, did I make a blog post about it? I actually was asking the question when I first bought a device that could do this, whether students actually cared. And I actually convinced myself that this looks a tiny little bit better. It just looks more like actual writing. But I don't know. I'm curious what others think. I can tell that this is true drawing software because of the pressure sensitivity. It's actually changing the hue of the digital ink. Very cool.
And we can say that A is dv dt. So the derivative of position with respect to time is the velocity. The derivative of velocity with respect to time is the acceleration. So you could also remember that another way of writing this a bit simpler is by writing a little dot on the top.
Nice.
So s with a little dot means the derivative of s with respect to the time. So I could also write this as v with a little dot above it. But v is also s with a little dot, so literally all we do to indicate that it's the second derivative is just put two dots. So one dot.
And so you saw right there, one note, for example, that would have been bright white, might have been skinny, but it wouldn't have been bright white. What she actually had to do, I'll just go back and show that to you again. So let's just play that
Derivative
again.
is just put 2 dots.
Can't even see it when she first puts
So
it down.
1
That's
dot,
so interesting.
first time derivative, 2 dots, second time derivative. This is all well and good.
I'll say, by the way, that I just love this notation. It just saves so much space, and for handwriting, it's great. Now, if you're using something like LaTeX or something, I don't know which is faster. It might be faster to write the fraction, but it's clean, it's easy. It does, it tells its story quite fast. Especially when you're involving this in a more complicated equation, I think the dot notation works really, really well.
But we really want to have a think about it in terms of our x and our y components. So if we have a think, we know that, well, Vx is dx dt x dot, cool. So we know that Vy is y dot, cool. So if we think about, I have a velocity here with our Vx and our Vy. Please pretend that these are straight. I'm not very good at drawing, as you can see.
Please pretend that these are straight.
No overall velocity, so this should be a right angle. And just from Pythagoras, we know that to find the magnitude of this vector, it's just the square root of Vx squared plus Vy squared. In other words, we can write V is equal to the square root of x dot squared plus y dot squared. So why am I showing you this? It's because we write our kinetic energy, we write K is equal to a half.
So I just have to pause and talk a little bit about this shape of the letter X. So I know a lot of people who write their X's this way, and if you watched how she wrote it, right, it's a stroke and then another stroke. It seems to me that from an efficiency of mechanics perspective, that is several changes of direction. And so if you compare that to the way that for example, I write an X where it's just like droop, droop, where you actually make a cross, like the multiplication sign, I think it's way more efficient to write. Now, I actually think this looks cleaner. This looks really, really nice, and it looks a little bit more typeset. The reason I raise it, though, is X is, of course, the most common letter in mathematics. Is that true? I'm going to declare that's true. And so I would guess that the people who first sort of started doing that probably wrote their X's this way. And so it's interesting to choose something that probably is a low efficiency stroke to write all the time. So that's fascinating to me. Never really thought about that before. Because if you watch, every time she writes an X in here versus a Y, the X takes her twice as long as it takes her to write a Y, it seems like. So let's keep watching that. It's super, super interesting.
mv squared. However, we want to write it in terms of the derivatives of our position. So it's best when you're working with Lagrangians to try to limit yourself to as few variables like this as possible. You can also write this as a half m and then square root of x dot squared plus y dot squared, all squared. Square roots cancel out, and you get k is equal to a half m bracket x dot plus y dot, and both of them are squared.
Whoa, she wrote the X the other way that time. Okay, that was weird. That was weird. I didn't think people ever did that. Super interesting.
So now let's have a look at finding the
Very
Lagrangian
cool.
of a couple of systems.
Very cool.
So I've got Lagrangian written up here. So we've got L is equal to T, which is the kinetic energy, minus V, which is the potential energy. So now let's have a look at this first system. This is a pretty simple one. It's just an object falling from rest under the influence of a gravitational field. So you've done a lot of this already. I just wanted to show you this kind of as a sanity check, just to prove to you that yes, Lagrangian mechanics really does just give you exactly what Newtonian mechanics does, just in a different way, and in some cases a slightly easier one. So we know that L is equal to T minus V. So our first port of call is to find T. So this is system's only got one object. It's just got this one ball falling down here. And we know that the kinetic energy of that is just of an object is going to be a half mv squared. Remembering that, in fact, we can write our velocity in terms of our position, and we know that the velocity is entirely in the y direction, we can write this as a half m y dot squared.
So I'm just going to pause right there and comment about how, we usually in the introductory physics sequences, we talk about how really having to nail your axes before you start. Let's say, okay, well, positive x to the right and positive y is, let's declare it to be up, let's say, or down. And it's really, really interesting when you do the Lagrangian stuff. You think about how, my God, I keep squaring everything. It doesn't seem like it matters which way y goes. And wait a minute, how can it possibly know which way it falls? And that, of course, that has to do with how she's going to decide to write the potential energy, right? But it's interesting that half of the work, right, this half, it doesn't matter, right? It's like, it's just squared, so it doesn't, you get the exact same term going up or going down, and all of the directionality of this problem, sort of the direction of the force, is all buried here. And this happens, I mean, it's going to happen down here too, right? The kinetic energy is going to be really strange. It doesn't matter if it's going to the right or to the left, to the right or to the left. There's several different scenarios that are going to have the exact same kinetic energy, but the potential energy is going to really declare, and then of course this placement of this sign, which I guess is connected to how we actually define the Lagrangian. Oh, that's not true. That comes from the calculus of variations. So I think you have to have this. You can't just be arbitrarily choose a different sign here. So anyways, I've always found it interesting that our approach on the Lagrangian side is so different because we don't care as much about the directionality until we get to the second term.
So now, looking at the potential energy, I'm sure this will come as no surprise to you that it is the gravitational potential energy. So that's simply written as mgy. So putting all of these together, I can write my Lagrangian. L is equal to a half my dot squared minus mgy. So that is the Lagrangian for a object falling under a uniform gravitational field.
All right, I'm just going to fast forward to see, how ugly this one gets, because I assume she's just going to do the same thing here. So let's just fast forward until we see it. I'm not sure if it's actually happening. Yes, it is. Okay, there we go. Okay. Okay, so she's using a capital X and a lowercase x here. Interesting. So again, noting, by the way, this different way of writing x's, because they look so different, we're not going to get super confused about who's capital and who's lowercase. That's really, really interesting. All right. Okay, so yeah, so she actually has the whole thing set to go, and we now have 3 variables. Except that, this is really, really interesting. What's not built into this yet is this constraint. And so this is how you'd set up the Lagrangian, but we don't actually have 3 degrees of freedom in this problem. We really only have 2. It's really just this and this. And I'm sure she says that, but it's fascinating that from the perspective of this video, which is just to set up the Lagrangians, you have a tiny little bit more work to do to sort of get this constraint built in. Very, very cool. All right, so I thought the setup was great. I think that the description about where we're coming from was really cool. The particular example of of essentially this that she had set up when she first started, that was really, really cool too. So loved it. All right, everybody. Well, hope you have a great day. And remember, physics teachers are awesome.